In the first part of today's lecture, we're going to finish discussing kinetics. So we'll first look at catalysts and how they affect the rate of reactions by affecting the activation energy. And then we'll look at the concept of reaction mechanisms and how the mechanism relates to the overall reaction, and also predict rate loss for a reaction based on a simple mechanism and identify the slow step, the rate determining step. So we've already seen that collision theory of reaction rates can be used to explain the factors that affect reaction rates. So in order for a reaction to occur, there are three criteria that must be met. The first is that the reacting molecules must collide with each other. So this is going to be affected by the phases of the reactants. So molecules or particles in the gas phase are going to be moving more rapidly and so are more likely to collide with each other, whereas molecules in the solid state are fairly fixed in location. So that means that reactions in the solid state are going to be relatively slow compared to reactions in the liquid state, and that's slower than reactions in the gas phase. And then we've also seen that reaction rates are affected by concentrations of reactants. So if we have higher concentrations of reactants, we're increasing the chances that they're going to collide with each other. So additionally, when the molecules collide, they have to collide in a specific orientation. So they have to collide such that atoms are rearranged and form bonds, the bonds that are present in the products. And then lastly, the energy of the collisions is important. So there's a minimum energy that must be overcome for a reaction to occur. This is the activation energy. And so the colliding molecules have to have as much kinetic energy, at least, as the activation energy, or more than that. And so that means that temperature and kinetic energy of particles affects whether or not a collision leads to a productive reaction. So just because molecules collide doesn't necessarily mean that they result in formation of products. So last time we looked at reaction coordinate diagrams, which basically show us the relative energies of reactants to products, as well as the transition state, which is a higher energy species that must be formed in order for the reaction to occur. And so in these diagrams, we can identify that the enthalpy change for the reaction is the difference in energy between the reactants and products, so shown here. And the activation energy is the difference in energy between the reactants and the transition state. So the enthalpy of the reaction will be related to the thermodynamics of the reaction and how many products form. The activation energy is related to the rate at which the reaction actually occurs. So we saw on Thursday that the Arrhenius equation relates the rate constant K to the activation energy, and if we know K values at two different temperatures, we can use those rate constants and relate them to temperature to find the activation energy of a reaction. And so this means that by just measuring two rate constants at two different temperatures, we can evaluate activation energy. So we looked at this example towards the end of class on Thursday, and we saw that if we know the activation energy, we wanted to predict how much faster the reaction would occur at 80 degrees versus 20 degrees. So we know that rate and rate constants are related to each other through the rate law. So the general form of the rate law is just that rate is equal to K times concentrations of reactants raised to some power, the order of the reaction. And so that means the rate is proportional to the rate constant. And so if we know the ratio of the rate constants, which we can get from the Arrhenius equation, we know the ratio of the rates at the two temperatures. So that means that the ratio of the rate at 80 to the rate at 20 is going to be equal to the ratio of the rate constants. And so we can find that ratio using the Arrhenius equation. So we know that the natural log of K at 80 over 20 is going to be equal to the activation energy divided by the gas constant R, which in this case we want in kilojoules per mole K, times 1 over the second temperature, the higher temperature, which we have to convert to Kelvin, So that comes out to 3.49. And so to solve for the rate constant at 80 over 20, we just take E to 3.49, which comes out to 32.7. And so that means that at 80 degrees, the reaction occurs about 33 times faster than it does at 20 degrees. So we've seen various factors that affect reaction rates. We know that the nature of the reactants affects the rate, the concentration of reactants, and the temperature affect the rate. And the last piece that we haven't looked at is the functioning of a catalyst. So a catalyst is a substance that increases the rate of reaction, but it's not actually consumed in the reaction. And it acts basically by lowering the activation energy of the reaction. So it does this by basically creating an alternative pathway for the reaction that has a lower energetic barrier or activation energy. And so it's involved in the reaction, but it's not consumed. And this means that the overall stoichiometry of the reaction isn't changed by the presence of a catalyst. And this also means that the thermodynamics of the reaction are unchanged. So only the activation energy and therefore the rate is affected. The catalyst is transformed during the course of the reaction, but it's regenerated when the reaction is complete. So this is an example of a reaction that occurs at a faster rate when it's performed in the presence of a catalyst, in this case iodine. So this is a simple isomerization reaction where we're taking cis-2-butene and converting it to trans-2-butene. So the difference between these two is that in the cis isomer, the two CH3 groups are on the same side of the double bond, but in the trans isomer, they're on opposite sides. And the reason that this is a high energy process relates back to something that you covered last semester, which is hybridization of orbitals and valence bond theory. So in cis-2-butene, we have a double bond between two carbon atoms. And so that double bond is formed by a sigma bond between two sp2 hybridized carbon atoms. And then also a pi bond between two p orbitals. And these pi bonds are perpendicular to the sigma bond. And so in order for rotation around that double bond to occur, that pi bond has to break, because if one of the pi bonds gets rotated out of the plane, that will lead to a decrease in overlap of orbitals and therefore breaking of the bond. So this is a relatively slow reaction because of the fact that we have to break a fairly strong pi bond in order for rotation to occur, but the rate is increased by the presence of iodine in the reaction mixture. So this shows basically the process that is proposed to occur when iodine catalyzes this reaction. It's a catalytic cycle or a mechanism. So it's proposed that the first step involves just cleavage of the iodine-iodine bond in I2, and then it's actually the iodine atom that's catalyzing the reaction. So in the first step, the iodine adds to the cis-2-butene, which ends up breaking that carbon-carbon double bond. And then once that bond is broken, there is free rotation of the carbon-carbon single bond, and so the location of the methyl groups switch. And then the iodine atom dissociates, and in the process of doing so, reforms that double bond and regenerates the iodine atom. So based on this mechanism, we can write a rate law for the reaction. So the balanced overall reaction isn't actually changed. We're still starting with cis-2-butene. And converting to trans-2-butene. So the iodine isn't included in the balanced reaction because it's not consumed. However, the iodine is going to be in the rate law. So it turns out that based on experiment, the rate law for the reaction is the rate constant times the concentration of the cis-2-butene times the concentration of molecular iodine to the 1/2. So the order in molecular iodine is 1/2. And the iodine is included in the rate law in this case because it has an effect on the reaction rate. So the reaction coordinate diagram for this reaction looks a lot different than the reaction for the uncatalyzed reaction. So the reaction coordinate for the uncatalyzed reaction is shown in black. And what's important to note is that the energy of the reactants and products isn't actually particularly different. So just judging solely by the energy of the cis versus the trans product, we would expect that conversion between the two should be quite easy. But it's actually a very slow reaction because the energy of the transition state is quite high. So this would be the transition state for the uncatalyzed reaction. And so the reason that the reaction is so slow is because this transition state is so high energy, the colliding particles have to have high energy in order to get over that or through that transition state. Now for the catalyzed reaction, we see that basically, rather than it occurring all in one step, it's broken down into 5 different steps. And all of the energies of these intermediate and transition species are much lower. So none of the energies of the individual steps are nearly as high as the activation energy for the uncatalyzed reaction. So this first step, to form intermediate 1, has the highest activation energy because the activation energy would be this energy shown here. And so that step is the rate determining step. All of the other steps are easier than that because they all involve activation energies that are lower, and so they all occur much faster. So the catalytic reaction is one case where we illustrate a reaction mechanism. So a reaction mechanism is just a series of bond breaking and bond forming steps that occur during the conversion from reactants to products. And these bond making and breaking steps are referred to as elementary steps, and each of the elementary steps have to add to give the overall stoichiometry of the reaction. So this illustrates an example of a simple reaction mechanism where we have reactants A and B reacting in the first step to form X and M, and then another equivalent of A reacts with M to form Y. So the overall balance equation is just the sum of the two reactions. 2A plus B goes to X plus Y. So in this mechanism, steps 1 and 2 are examples of elementary steps. And when we're working with elementary steps, we're able to write a rate law directly from the stoichiometry of the reaction. Now, the only reason that we can do this is because elementary steps always occur in a single step. And so we can determine the reaction order based solely on the stoichiometry. So if we call the rate constant for step 1 K1, the rate for step 1 would just be K1 times the concentration of A times the concentration of B. And then if we call the rate constant for the second step K2, that rate would be K2 times the concentration of A times the concentration of M. So again, we can only write rate laws directly from the stoichiometry of a reaction when it's an elementary step. Now in this mechanism, there are a few new species. So in step 1, we form M, but in step 2, M reacts with A to form Y. So M is an example of an intermediate. So M is a species that's formed in one step, but then it's consumed in another. So generally speaking, intermediates are high energy, and they don't last long, so they're short-lived. And so this means that they're hard to detect. So it will be hard to actually measure the concentration of M at the beginning of the reaction because it's not going to stay around for very long. So a couple of other terms that are related to reaction mechanisms. The first is what's called the molecularity of the reaction. So if we have a single reactant converting to a product, this is a unimolecular elementary step. If we have two reactants reacting to form products, the reaction is bimolecular. In the first case here, we have two different reactants reacting, so the rate is equal to the concentration of A times the concentration of B. But if we have a reaction like this third case, where we have two molecules of A reacting, this is still a bimolecular step because two molecules are reacting, but the rate law would be the rate times the concentration of A squared. And then the third type of reaction is a termolecular, where we have two molecules of A reacting with B. Now, termolecular reactions are fairly uncommon because if we think about what needs to happen for a termolecular reaction to occur, we need to have three different reactants collide at the same time, and they all need to be oriented in a way that gives us the proper orientation to form products, and then they also have to have enough energy to overcome the activation energy. So the most common types of elementary steps that you'll see are unimolecular or bimolecular. And then the rate law for the reaction is determined by the rate law for whichever step is slowest. So the slow step is referred to as the rate determining step. Which sometimes we'll abbreviate as RDS. And this is going to be the step that has the largest activation energy, because the largest activation energy is going to lead to the slowest rate. So reaction mechanisms can be proposed based on experimental techniques, and it can never be definitively proven. It's just a proposal of how the reaction proceeds on the molecular level. So a few criteria when evaluating reaction mechanisms are that the elementary steps have to add to the overall balanced equation, and the rate law for the mechanism has to be in agreement with the rate law that's determined experimentally. And there may be more than one mechanism that agrees with both the reaction stoichiometry and the kinetics, and there's no way to definitively prove which is correct. So we'll look at a few different examples of mechanisms. In the first case, we have a mechanism where the first step is the rate determining step. So that means that the overall rate of the reaction is going to depend on the rate of that first step. So we can write rate laws for both of the two steps. So we'll call the rate constant for step 1 K1. And so that means that the rate is equal to K1 times the concentration of A times the concentration of B. And so this is going to be the rate law for the overall reaction. So this reaction is going to be first order in A and B. And second order overall. And so it's a bimolecular reaction because it depends on collision of two particles, A and B. So we'll look at another example of an actual reaction and its mechanism. So the reaction of NO2 with carbon monoxide is proposed to occur in two steps. In the first step, two molecules of nitrogen dioxide react with each other to form nitrogen monoxide and nitrogen trioxide. And this step is slow and it's an endothermic reaction. And then in the next step, nitrogen trioxide reacts with carbon monoxide to form nitrogen dioxide and carbon dioxide, and this step is fast and exothermic. So we first want to know what the overall reaction is, and so in order to write the overall balance equation, we have to look at the two individual steps and add them together. So in the reaction, we have 2NO2 reacting in the first step. In the second step, we have NO3 and carbon monoxide reacting. And then for our products, we have nitrogen monoxide and NO3 forming. And then in the second step, nitrogen dioxide and carbon dioxide forming. So to write the overall balance equation, we need to look for any species that are present in the reactants and the products because they'll cancel. So we see that we have 2 NO2 in the reactants and 1 in the products, so that means one of those is going to cancel in the reactants. And then we also have NO3 in both reactants and products. So from this we can write that the overall reaction is nitrogen dioxide plus carbon monoxide to form nitrogen monoxide and carbon dioxide. So in this mechanism, we have one intermediate species. It's going to be the nitrogen trioxide because it's formed in the first step and then consumed in the second. So that means that the rate law for the reaction is going to be the same as the rate law for the first step. So the rate for step 1, which will be equal to K1 times the concentration of NO2 squared. So we basically want to be able to describe this mechanism through a reaction coordinate diagram. So we're told that in addition to knowing the balanced overall equation, we know that the overall reaction is exothermic, and we want to draw an energy diagram for this. So in the reaction coordinate diagram, if you recall, we plot the reaction progress versus the potential energy. So we know that the overall reaction is exothermic, so that means that energy is released in the course of the reaction, and so that means that the reactants must be higher energy than the products. So we start by drawing our reactants, which are NO2 and carbon monoxide. And then we know that our products must be lower energy. So NO and CO2. And we know that as the reaction proceeds, the various transition states and intermediates will have to form. So we know that the intermediate species are going to be the products of the first step. And we know that the first step is endothermic, so we know that the energy of nitrogen monoxide and nitrogen trioxide must be higher than the energy of the reactants. So we'll draw them about there. And so we know that this must go through a transition state that's high energy. And then in the second step, another transition state is formed, and then our products form. So we can identify a few different values and species in this mechanism. So at the top of this energy barrier would be the transition state for step 1, and the difference in energy between those two, so between the reactants and transition state 1, is going to be the activation energy for step 1. And then we know that the next transition state would be number 2, and the difference in energy between those two is activation energy for step 2. And the way we've drawn this makes sense in terms of the mechanism, because we know that the first step is the slow step, so that means that the activation energy for step 1 must be higher than the activation energy for step 2. And we can also fill in some of the thermodynamic values within this mechanism. So the difference in energy between the reactants and the products in step 1 will be delta H for step 1. And the difference in energy between the intermediates and the ultimate products will be delta H for step 2. And we know that the difference in energy between reactants and products will be delta H for the reaction. So this energy reaction coordinate gives us an overview of the energetic relationships between reactants, products, transition states, and intermediates. So we've now looked at a few different examples where the first step of the mechanism is the rate determining step, but this won't always be the case. We looked at that first because it's the simplest case. So an alternative mechanism is that we have A and B reacting to form intermediate M, and that's the fast step. And then that's followed by a slow step, which involves reaction of A with M. So step 1 is the fast step, and we'll call the rate constant for step 1 K1. So that means that the rate for step 1 is K1 concentration of A, concentration of M. Concentration of B. And then rate 2 is K2 concentration of M times the concentration of A. So now because step 2 is the slow step, that's going to be the rate determining step. And so that means that the rate for the overall reaction is equal to the rate for step 2. Now, as I mentioned before, intermediates like M are high energy and difficult to detect, and so we can't really do much with a rate law that's expressed in terms of concentration of M because we can't measure the concentration of M. So it would be difficult to measure the rate of the reaction and see how it depends on the concentration of M and A. So basically, we want to be able to write the rate law in terms of reactants and constants and not include any intermediates in the rate law. So in order to do this, we need to think about kind of what's actually going on as the reaction proceeds. So step 1 occurs very quickly, and so M is rapidly formed, but then it takes a while for it to be consumed in the second step and reform Y. So during the course of this process, it's possible that some M converts back to A and B in the reverse reaction. So we'll call this reverse reaction constant, rate constant, K minus 1. So over time, an equilibrium is established between A and B and M. So that's going to be established before step 2 occurs. And so when a dynamic equilibrium is established, we've seen this quite a bit when we talked about vapor pressure, for example. When the reaction first starts, we don't have any M and we only have A and B, so the forward reaction occurs rapidly. But then as M's concentration is increased, some will convert back to A and B. And this process continues until the rate of the forward reaction is equal to the rate of the reverse reaction. So we'll call that rate forward is equal to the rate of the reverse reaction. And so with this equilibrium established, we can express the rates of the forward and reverse reactions. The rate of the forward reaction will just be the rate law for the forward reaction that we wrote. So K1, concentration of A, concentration of B. The rate law for the reverse reaction will be K minus 1 times the concentration of M, because in the reverse reaction, the only reactant is going to be M. So now we can rearrange this equation. So if we divide both sides by K minus 1, and then divide both sides by concentration of A times the concentration of B, we now have a constant, so the ratio of the rate constants, equal to concentrations of intermediate and reactants. And it turns out that this ratio of K1 over K minus 1 is a specific constant called the equilibrium constant. And this is designated with a capital K. And so what this allows us to do is express the concentration of M, the intermediate, in terms of the equilibrium constant K and the concentrations of reactants. So we can rewrite this as concentration of M is equal to the equilibrium constant times the concentration of A times the concentration of B. And so now we have concentration of M expressed in terms of measurable values. So we could determine the equilibrium constant, and we can measure concentrations of A and B because we know how much we're starting with. So basically we can substitute this back into the rate law. So we know that the rate is equal to K2 times the concentration of A times the concentration of M. And so we can substitute in our expression for M. And we can kind of group the two constants, K2 and K, the equilibrium constant, into a new constant that we'll just call K prime. And then that's going to be multiplied by the concentration of A squared times the concentration of B. And so this gives us a rate law that is expressed in terms of concentrations of reactants, which is a measurable value.